Hello everyone, my name is Ishwar Rai, Sikkim Government College Nancy from second semester. First of all, I would like to give a thanks to Physics Department and Dr. C.P. Khatiwara who gives me an opportunity to present a presentation about cantilever. A cantilever is a rigid structural element that extends horizontally and is supported at only one end. Typically, it extends from a flat vertical surface such as a well to which it must be firmly attached. Like other structural elements, a cantilever can be formed as a beam, plate, truss or slab. Now we have these three schematic images. The top example has a full moment connection like a horizontal flagpole bolt to the side of a building. The middle example is created by an extension of a simple supported beam, such as the way a dividing board is anchored and extends over the edge of a swimming pool. The bottom example is created by adding a robin bonding condition to the beam element, which essentially adds an elastic spring to the end board. The middle and bottom example may be considered structurally equivalent depending on the effective stiffness of the spring and beam element. Now we have a diagram here. A horizontal beam fixed at one end and load at the free end is known as cantilever. Now this is the beam, horizontal beam. When we apply load here, W, this is the load, and it will bend like this. And this type of beam is known as cantilever beam. L is equals to length of the horizontal beam. Let a beam be fixed at A and loaded at the end B. Under the applied load W, and B is deflected to B. Unbent horizontal axis of beam is along x-axis and y-axis is vertically downward. For a section beam at distance x from fixed end A, the moment of bending couples under the load we can be given as tau is equals to W into L minus X, and L is the length of beam, this X is a distance, and L minus X is a bending, this is the bending portion, and then the torque acting on this beam is tau is equals to W into L minus X. Since cantilever is a equilibrium in the bend position, hence the bending couples for the said section must be balanced by restoring couples or bending moment at the considered section. Yi by R is equals to W into L minus X. This is equation 1, where Yi by R is equals to tau. Tau is bending moment, where Y is equals to Young's modulus, I is equals to moment of inertia, R is equals to radius of curvature. For Y depressions of the beam at a distance x from the fixed end, the radius of curvature BR within the bracket 1 plus dy dx square and whole square 3 by 2 divided by d square y by ds square. This is the standard formula. Since this y is very small, so we have to neglect it. Since y is very small, so it neglect in comparisons to 1. So numerator expressions is neglected. R is equals to 1 by d square y by dx square. Now put the value of R in equation 1. In this equation 1, yi d square y by ds square is equals to w into L minus x. D square y by dx square is equals to w by yi into L minus x. This is equation 2. In order to get the depressions at free end at x is equals to L, now we have to integrate. Integrating equation 2, dy by dx is equals to w by yi. Integrate L minus x, and this is the second order depression equation, and this is the first order depression equation. And dy by dx is equals to w by yi into Lx minus x square by 2 plus c1. C1 is the integration constant. This is the equation 3. Hence c1 is the constant of integration using boundary condition is x is equals to 0. dy by dx is equals to 0. Therefore dy by dx is equals to w by iy into Lx minus x square by 2, and this is equation 4. It is to be pointed out that at P the slope of curvature tan theta, dy by dx, theta being the angle between x-axis and tangent at P of bend position APB dash, and dy by dx is equals to tan theta is equals to w by yi into Lx into x square by 2. This is equation 5. Now we also here we have to integrate. Integrating equation 5, y is equals to w by yi into Lx square by 2 minus x cube by 6 plus c2. This is x. This x, when we integrate it will x square and by 2 minus x square, it will be x cube by 3 into 2 6, where c2 constant of integration constant of integrate is x is equals to 0, y is equals to 0, then c2 is equals to 0. When this LHS is also 0 and RHS is also 0, c2 is equals to 0, also 0. Same equation but without c2, y is equals to w by yi into Lx square by 2 minus x to the power cube by 6. This is equation 7. At last, at x is equals to L, let y is equals to y naught. Say y naught is equals to w by yi into L cube by 2 minus L cube by 6. Now we have to replace x is equals to L and y is equals to y naught. Y is equals to w, y is equals to w by yi into L cube by 2 minus L cube by 6. By replacing x is equals to L, it will be L cube, and this also L cube is equals to w by yi into L cube minus 2L to the power cube divided by 12. This equation 8. This equation we get by LCM. W by yi 4, L cube by 12, and now y naught is equals to WL to the power cube by 3yi, and this is the equation 9. If the beam is circular, then y is equals to pi r to the power 4 divided by 4. Y naught is equals to 4 w L to the power cube divided by 3 pi 4 to the power 4 y, and r is a radius of circular cross sections. Thank you.